Bismillahirrahmanirrahim. If you recall, last time we talked about composite transformations or compositions of transformations, and which basically means combination of any two or more transformations. And their transformations, if you recall, were of four types: translations, reflections, rotations, and dilations. So if you combine any of these, then you would get a composite or combinations of transformations. Today I just wanted to review what we talked about last time and also talk about dilation a little bit before we finish, inshallah. If you recall, we talked about this theorem last time. This is the reflections in parallel lines theorem, that if you have two parallel lines and if you were to reflect an object two times across these two parallel lines, and the result of these double reflections is basically a one long translation. So this is a double reflection across two parallel lines theorem, as affectionately known by myself. So reflections in two parallel lines. And if you remember, the theorem stated the following: that the composition of two reflections in parallel lines can be described by a translation vector, a single translation vector. And this vector is perpendicular to the two lines, because that's how we reflect. We reflect across perpendicularity, perpendicular to two lines, and twice the distance between the lines. So if we were to first reflect it, we would get this image. In this particular case, this triangle. You can call the whole triangle P, and the triangle P is reflected here to P prime. And if we do it again a second time, we get this P double prime triangle. Now, you can describe this double reflection, remember, using a long vector that would translate or slide or glide this blue triangle all the way up to the red triangle. In other words, you can just move this triangle over here to get a P double prime. So one single long translation will give you the same result as this double reflection. And the theorem said that the vector that does this, the vector that moves this triangle to this new location, to the red location, is the length of the vector is 2 times the distance between the two parallel lines. That is, the distance of the length of the vector is 2 times the distance d, if the distance between the two lines was measured thus. So this is what this particular theorem related to us. I wanted us to understand, at least have a good understanding as to why that might be. So if you look at this particular figure, with the first reflection, the blue and the green triangle, when we reflect a point across a particular line, you reflected the same distance. So this distance here is going to be the same distance here. That is, from here to here is going to be the same distance from there to there. So that's how we reflect, right? So this particular point, for example, if you reflect it, this distance from here would be the same as that distance over there. And then this distance here from there to there would be the same distance as from there to there. So that's the idea of reflection. So if you, for example, give this distance a name, let's call that A, and from here to here, that distance would also be the same, and that would be A, correct? So from this point to this point, it would be this distance here from this point to the line, and from the line to that point would be the same. That would be A. And then if you reflect it again for the second time, you will see that the distance from this point here, that distance will be the same distance over here, correct? Because that's the idea of reflection. You would reflect at the same distance. So if you call this distance over here, let's give that a name, you can call that B, because that's B over there. And this distance here would again be B, like that. So this distance is the same. If you call it A, you have to call that one A. And if this distance is the same, if you call this one B, this has to be the same as B. Then you will notice, of course, that this distance here is A plus B, isn't it? So D, you can rewrite D as A plus B. So let me give myself a lot of room over here. So you can say D is basically A plus B, isn't it? Because that's the length of D. And then the whole distance from here to here is 2 A's and 2 B's, isn't it? Right? So it's basically twice the A plus B, like that. So you can see intuitively, easily prove that in fact the distance, the length of the vector, in fact, is going to be two times the distance between the two lines. And then we also learned this particular theorem, and this was the reflections in intersecting line. Previously we had reflections across two parallel lines, and here we have reflections across two intersecting lines, or double reflections in intersecting lines theorem, or double reflections in intersecting lines equals rotation. So this theorem stated the composition of two reflections in intersecting lines can be described by a single rotation, and the single rotation was about the point of intersection P over here, and the angle that is twice the measure of the acute or right angle formed by the line. So the rotation would be twice as big as x over here, or 2x. So if we had an image like this, in this case segment A, and if you reflect this two times, first across the first line and then again across the second line, that is, if you reflect it two times, that's the same thing as one big rotation across point P, and the measure of that angle rotation was twice as the measure of angle x. So this is the second theorem that we learned last time. Okay, so I shall try to explain this to you, although this might be slightly beyond the material that we covered so far, so that at least we have some kind of intuitive understanding. So when you reflect the first time, let's just look at this particular point over here. When you reflect that first point and you reflect to a perpendicular distance that is congruent. So this point right here, that distance should be the same distance as over there, correct? And then if you were to reflect the second time around, that's the same principle would apply. That is, this distance here from that distance over there, try to do that perpendicular distance, should be the same distance as over here. So that distance is equal to that distance over there. Okay, so that's the idea of reflecting again. Now if we were to construct a little triangle over here, from here to here and from here to here, all right, then we have basically made two triangles right there like this. So here's a triangle and here's another triangle. The thing about this triangle is that these are right triangles, for one thing, because we always reflect across perpendicular distances, and these are congruent right triangles. That means they can be flipped on one another. So if that's the case, this angle over here, let's call this here angle A, this angle right here, all right, is this going to be the same as this particular angle of the other triangle, because they are congruent triangles. So this angle over here is the same as this angle over here. That's the little tiny angles over there. All right. Now if we were again to reflect the second time around, like over here like this, then again you form two right triangles that are equal to each other, congruent, because this side and this side are congruent, like, you know. So now we have two right triangles again. So these two angles, these baby angles right here and that baby angle right there, would also be congruent. So if you call this angle B for this triangle, this angle would also be B. Then you notice that x is basically right here. So x is going to be a plus b. So x here is a plus b. And the whole big angle rotation, the entire angle of rotation, is going to be 2x, because this 2x is 2 times a and 2 times b. So 2x is basically then 2 times a plus b. And you can see there are 2 a's here and 2 b's over there. So the angle of rotation is twice as x. So I just wanted us to have like a working intuitive understanding for why these theorems work. Okay, so the last thing I wanted to talk about is actually dilations. Dilations are transformations where either you enlarge the image or shrink the image, either like zoom in or zoom out type of a thing. So, and they're pretty easy actually. For example, if I were to take a triangle here, triangle ABC. So I have a triangle ABC over here, and I'm going to perform a dilation then with a factor of 2. So we say dilate triangle. So D-I-L-A-T, dilate triangle ABC with the factor 2. of 2. That means you kind of multiply the triangle, make it 2 times as bigger. Now, if you, as I suggested before, dilation can either means enlarging or shrinking. So both enlarging an object or shrinking an object are both called dilation. Okay, so zooming in or zooming out, they're both called dilations in geometry. So you can say factor of 2 would be like enlarging. A factor of a third would be like shrinking it by by 1/3 of its size. So either you enlarge or you shrink an image, they're both called dilation. So if you were to dilate this particular triangle with the factor of 2, then the easiest thing, but carefulest thing, would be just to write each vertices down so you don't make any silly mistakes. So A is -3 and -2, and B here is 1, 2, and C here is 4, -1. Now notice here each little box represents two units. So if we were to dilate each one of these by a factor of 2, you basically multiply each ordered pair by factor of 2 like this. So that's easy enough. So when you do that, you get this. So A becomes A prime. So -3 times 2 is -6. -2 times 2 becomes -4. So it's easy peasy. You multiply each ordered pair by the factor you multiply. So this becomes 2 and 4, and C prime will become 8 and -2. So multiply this by this by this by this, and every single little x and y by a factor of 2 to get the dilation. And then you just plot it out. So A prime is -6, -4. That's -6 over here, and -4, that's like here. So that's A prime. And B prime is, let me just label this, so that's -6 and -4. B prime is 2, 4, so that's 2, and that's 4 right there. That's B prime, that's 2 and 4. And C prime is 8, -2, so that's 4, and that's 8 over here, and -2 is right there. So 8, that's C prime over here is 8, -2, and I can connect these three, and I'll have my new triangle A prime, B prime, C prime. So there is my dilated image like that. Ta-da! So it's pretty easy. You kind of like, made it bigger over here, and so the dilations tend to be reasonably easy to perform. Now you notice one thing. When you dilate an image, you make it bigger or smaller, right? The size of each particular triangle changes. Whereas when you do the other transformations, translations, reflections, and rotations, the size of the image does not change. It remains the same size. So these three transformations, the translations, reflections, and rotations, they are called isometric. Okay, isometric, meaning that the size of the image does not change. And dilation is non-isometric. Okay, so it's not isometric. The size of the image changes, or it's called non-isometric. So iso means the same, metric means the size of a thing. So whereas translations and reflections and rotations are isometric transformations, dilation is non-isometric. That is, it does not retain the size. That's the whole idea. You either make it bigger or smaller. And so that's dilation. With that, we complete our study of transformations for now. Until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.